Hi, everybody. Welcome back to Dave's Math Channel. I'm your host, David Tear, and this is my continuing feature on the Math Lovers book. And today I'm starting a new section. This is section 5.5 of chapter 5, which is on sets. And this section's on functions, which are special type of relation. I talked about relations. That's what was in section 5.4, the previous section. So I'm going to do, I think, a total of 5 videos on functions. Functions turn out to be very important. I mean, I'm sure you guys have used them, but you probably don't know the formal definition of a function, which requires knowing what set is, in particular, knowing what relation is. So anyway, let's begin. So what is a function? First, I'm going to define a function, and I think I already kind of did in my previous video, or maybe one of my previous videos. A function is a special type of relation, and if you guys remember what a relation is just a set of ordered pairs of elements x comma y, where x belongs to a set capital X, an arbitrary set, and y belongs to an arbitrary set capital Y. That's all a relation is, just a set of ordered pairs with elements from two different sets. They could be the same set, they don't have to be. And a function is a particular type of relation, but it's a relation where you never have two elements of the form x, y1, x comma y1, and x comma y2. If you do have those, then you have to have y1 equals y2. You can't have two different values of y correspond to the same value of x. And if you were doing this graphically, I mean, if your sets were domains of numbers, then what that would mean is when you graph a function, you probably learned this when you're learning about functions. Any vertical line on your graph can intersect as most one point on the graph of a function. So that's what a function is. And anyway, now I'm going to go over some examples. So for our first example, I give kind of an arbitrary relation I call R1. That's just a set of four ordered pairs of numbers, and it doesn't really matter what the domain is here, as long as it has these four ordered pairs. So the ordered pairs are 0, comma 0, 1, comma minus 1, 2, comma 3, and 3, comma 4. If you like, you could graph this relation because it is just a set of points, and you can graph that on a piece of graph paper if you like. But the question asks whether this is a function, and the answer is yes, because you'll notice that each value of x in this relation is unique. We have x equals either 0, 1, 2, or 3. Therefore, we don't have two of the same values of x, which could have different values of y. We don't have that, so this is a function. And actually, I should say one more thing about functions. I know that functions, the formal definition of a function is confusing to a lot of people for a lot of good reasons. I mean, I think functions are kind of intuitive. The way most people think of functions, this is the way I like to think of functions too. Think of a function as a machine or like a computer program. As a matter of fact, every computer algorithm, every program can be written as a function, it turns out. And a function is just something that takes an input and spits out an output. The output is the value of the function, it's the value y. So if you like, your input is your x and your output is your y. And there are things called multivariate functions, which I'm not going to get into yet here. But you can even think of multivariate functions as a special type of functions, just that your input are not just single numbers, they're sets of numbers or antiples of numbers, tuples of numbers, if you like. People sometimes talk about multi-valued functions. I don't really like that name because that kind of contradicts what a function is. A multi-valued function is really just a relation. And if you don't want to worry about multi-valued functions, forget it, just set that. But anyway, let's continue. For our second example, this is basically the same as the first example, except I'm adding another point to this relation, namely the point 2 comma minus 3. And now I think you can see this is no longer a function because we have two values, the same value of x, two points in our relation, or two elements of our relation that have the same value of x but different values of y, namely minus 3 and 3. And I think, by the way, anyway, think of a function as a machine. I mean, I think it's kind of obvious why a function has to have a unique value of y. Otherwise, it would not have a unique output. And that would mean that your computer program wouldn't always output the same thing, or maybe it's kind of an ambiguous output. Actually, it turns out quantum computers are like that, but I don't want to get into quantum computers here. Classical computers always spit out a single output. So that means they always work with functions. Every computer program can be thought of as a function, but not a relation that's not a function. Kind of has to be a function, otherwise it wouldn't be a classical algorithm because you want one answer. There's supposed to be one answer to the question you're asking a computer. I know in life there's not always one answer to every question. That's part of. I think that's a big part of what makes life interesting. But I guess maybe we should be grateful that life is like that. It's not like a computer program, because then everything would be completely predictable. Everything would be deterministic. I'm not going to get a whole philosophical debate about whether or not the universe is deterministic. I happen to be a non-determinist. I believe in free will. So I don't think that every input in the universe results in always the same output. Also, that doesn't seem to be the case in quantum mechanics. But I'm digressing quite a bit here. I like to do that sometimes. I don't know why. Anyway, for the third example, let's say our sets, our x and y are both the sets of real numbers. And now we're saying x r3y if y equals x squared. So all of our intuples for this relation, all our pairs, ordered pairs, have the form x comma x squared. Well, I think it's pretty easy to see this is a function. It's just a function y equals x squared, or f of x equals x squared. Every value of x gives you a unique value of y, namely x squared. That's a function. Pretty easy to see. But now for the fourth example, let's say, suppose we do it the other way around. I think I have to go to the next slide for that one. So suppose where our relation is x equals y squared. Well, now this is no longer a function, because as long as our domain is real, we could start with, for instance, the element 9 comma 3, but then 9 comma minus 3 also works. So I think you can see that in general, you get two values of y for a given value of x, because there's two square roots. There's a positive square root and a negative square root. So this is not a function. You can make it a function by restricting it to the positive, y to, making a restriction where y is not negative. That turns it into a function. And usually you can do this. I mean, usually when you have a relation that's not a function, you can restrict the range so that it does become a function. And actually a lot of useful cases that inverse trig functions are like that. Inverse trig functions would not be functions if you didn't restrict the range. And most inverse functions that people study in math are not technically functions, because you have to first restrict the domains. And square root's an example. Anyway, the fifth example. Again, our domain and our range are the sets of real numbers, all real numbers, and our relation, we say x r5y if and only if x squared plus y squared equals 1. And I went over this example, I believe, in my last video. This is just a unit circle. The set of points x squared, x comma y, where x and y are both real, and x squared plus y squared equals 1. That's the equation of a circle of radius 1. And you can see that pretty easily by graphing it, which I'm not doing here. But this is not a function, and I think I even mentioned this yesterday. A circle is not a function because in general, if you intersect your circle with a vertical line, you get two intersection points, not just one. And in this particular case, if you were going to solve for y in terms of x, you would get y equals plus or minus the square root of 1 minus x squared. And this example is kind of like the previous one. You can make it into a function if you restrict the range to be, say, non-negative. If you said y was the positive square root of 1 minus x squared, this is a function whose graph looks like a semicircle. Similarly, if you restricted the domain to be, the range to be negative, non-positive values of y, then you would get y equals minus square root of 1 minus x squared. That's a function too. But without those restrictions, it's a relation, but it's not a function. So anyway, that should give you an idea what functions are. And I think it's probably, I mean, it's good to have a formal definition of a function in terms of sets, because everything in math has to be well defined. I mean, a lot of times you kind of know what you're doing without, specifically defining all your terms, but that can lead to problems. I mean, in general, if you want to really nail everything down in math, especially if you want to prove things like prove theorems, prove results, it's very important to have precise definitions of everything, you know. So that's why we're defining functions formally in terms of set theory. But, if you want to think of functions in a more intuitive way, think of them as machines, which is the way I like to think of them. Anyway, that concludes my video for today. Thank you for watching. Long live math, and I'll see you guys next time. Bye.